is the sixth video lecture in a series of lectures on computational hydraulics. Last class we were talking about Euler's method. Euler's method is one of the simplest numerical techniques for solving ordinary differential equations. It essentially assumes a straight line representation of the differential equation, basically. It could easily be derived from the Taylor series expansion using the first two terms, essentially. So dy per dx was represented as the derivative form, dy per dx as delta x approach to 0, approach to dy per dx. So dy per dx is represented as the functional derivatives of y in x. So y at x plus delta x is approximately equal to y at x plus the derivative of y at x times delta x. So remember, f of x comma y is derivative. We have tried to solve an example on this, a couple of examples. And we have tried to see this example where we have tried to solve how long it would take to empty the tank of a cylindrical shape with 100 meters diameter and the initial depth of 5 meters. So it has got an outlet nozzle with a cross-sectional area of 0.3 meters square. So we have tried to show from continuous principle and using the air loss coefficient, air loss equation derived from the energy equation, we have tried to show that change in h per change in t is equal to negative A over capital small a over capital A times the velocity of flow through the outlet nozzle. And using that representation for the velocity for the outlet of the nozzle, you can essentially say, and representing negative A over A capital A times radical of 2g over 1 plus epsilon by k. So essentially, the h per dt is equal to k times square root of h, essentially. And then using Euler's method, we are trying to represent the slope essentially k times radical h. And then we have iterated a bit, try to find the value of h, approximately like 8.5 hours or 8.66 something hours is required to empty the tank. We have tried to show it. Now that was Euler's method. We can talk about improved Euler's method. In case of improved Euler's method, we are not going to use the slope, which is derived at the initial point only. But we are going to include an estimate of the slope, which is going to be found at the end of the steps line, or delta x. At the end of delta x, we are supposed to find out the slope, and using the average of the initial estimate of the slope and the final estimate of the slope, then we are going to find yi plus 1 as yi plus half times the average of these slopes times delta x. So this would relatively enhance the solution from Euler's method. It's the second order accurate. So you can try to solve the same problem, but using improved Euler's method. Remember, all you have to do is you have to include here hi plus 1 equal to hi plus 1 over 2 k times radical hi plus k times radical hi plus 1. So essentially that should give you the estimate of the first you need to find hi plus 1 using the direct estimate from using Euler's method, and then plug it here, and then ultimately you can find the enhanced or improved value for hi plus 1. Now the other form is Runge-Kutta method. This is relatively a more general form of Euler's method, I would say. So you can say here phi, function of xi, yi, and the step size h is an incremental function. So we are not going to use just one slope here, but a number of slopes represented by a certain function. One of the very common types of Runge-Kutta techniques is the fourth order Runge-Kutta technique. We can talk about the first order, second order, fourth order, but the fourth order is very much common. So in Runge-Kutta fourth order, the incremental function or the slope is going to be a weighted average of slopes computed at 4 different points. Essentially, we're going to use K1, which is the slope at the initial or at the beginning point of the derivative at the beginning point of x1, y1. And then using this slope, we are going to extend graphically, we are going to extend the line until we go halfway to h, which is between xi and xi plus 1. That's the end point. The space difference is h, actually, halfway between xi and xi plus 1. So at h over 2, essentially, or xi plus half h, we're going to extend the value of y using a slope of K1, which we have computed before. So that should give you another point somewhere halfway between xi and xi plus 1. So at that point, we are going to estimate the slope. That would give you K2. Using this slope again, but starting from the same initial point, xn, yn, we're going to extend the line until we go halfway between xi and xi plus 1, but with a different slope. So this time, that point where we strike, we are going to calculate the slope. So the slope shall give you K3. Using this slope of K3, again, we start from the initial point and elongate the line with a slope of K3 until we meet at a point along y-axis at xi plus 1. And then estimate the slope there. So that should give you slope K4. Having slopes K1, K2, K3, K4, we are going to get a weighted average, giving more weight to K2 and K3, twice actually, more precise. So K1 just 1 weight, K4 1 weight, whereas K2 and K3 two weights. So all in all, K1 1, K2 2, K3 2, which is 5, plus K4 1, 6. So we are going to divide the whole slopes by 6 and then times h. So the term 1 over 6 times K1 plus twice of K2 plus twice of K3 plus K4 is essentially the weighted slope. So that is slope times h plus yn shall give you the value of 1 in the next time step. So this is Runge-Kutta fourth order. Now let's demonstrate this one with an example. Now we are asked to solve the initial value problem, du per dx, negative du plus x plus 4. Since it's a first order problem, ordinary differential equation, first order, because the highest derivative is just 1. So we need to have at least one condition to be able to solve this problem. So this condition is provided at the initial point, so it's initial value problem. So u0 is equal to 1. So we are asked to obtain u at 0.2 using h, or the step size of 0.2. So we are going to directly obtain the value at 0.2, starting from the value at 0, which is given as 1. So we are required to find out the value of the function u at 0.2. Now, for general ordinary differential equation u per dx, the slope or its derivative is f of at x and ux. So we are going to use Runge-Kutta technique, which we have explained earlier. Now, let's first find the initial slope, k1, at 0 and u0. u0 is basically 1. X is 0 and u0 is 1. So we are going to find f at 0, 1. So f at 0, 1 would indicate, as per the function, the derivative function given du per dx, negative tu 2u plus x plus 4. So negative 2 times u, which is 1, plus 0 plus 4 shall give us 2. We have found already k1. Using this value of k1, we are going to obtain first xn plus half h. Xn is 0, half h is 0.1, so 0 plus 0.1 is 0.1. Then yn plus half k1h. Yn is basically the value of u at 0, which is 1 plus half times k1, which is 2, times h, which is 0.2, shall give you 1.2. F of 0.1, 1.2, we are going to plug in the initial equation u for du per dx. So negative 2 times u, which is 1.2, which we have found, plus 0.1 for x plus 4 is equal to 1.7. So we have just found k2. Now let's find k3. That is the slope or the derivative at xn plus half h and yn plus half k2h. K2 we have already obtained. So xn plus half h, we just know 0.1, which is 0 plus 1 over 2 times 0.2. Yn plus half k2h is yn means u at 0 plus u at 0 is just 1. Half times k2, which is 1.7, times h, which is 0.2, is 1.17. So using u of 1.17 and x of 0.1, we can obtain the derivatives. F of 0.1, 1.17 is negative 2 times 1.17 times plus 0.1 plus 4, which is 1.76. Next, we find the slope at the end of the step size at k4. So k4 is xn at xn plus h this time, and it's at h. So xn is 0 plus h, which is 0.2, and yn plus, there is no half here, at the end of the step size, which is plus k3 times h. So k3 we have just obtained to be 1.76 times h is 0.2. So u0 is just 1 plus 1.76 times 0.2 is 1.352. So the function evaluation shall give us 1.496. Now we are going to obtain the weighted slope, which is 1 over 6 times k1 plus twice of k2 plus twice of k3 plus k4. Then we are going to multiply with the step size of 0.2 and then we are going to add U at 0. So that should give you U at 0.2 to be 1.3472. So we have tried to solve this problem using the initial value problem. We have obtained a more enhanced version if you just decrease the step size problem. Maybe the same problem you might work using h is equal to 0.1. But obtain U at 0.2. Now another problem. A polluted lake has an initial concentration of bacteria obtained the power of 7 parts per meter cube, while the acceptable level is only 5 million parts per meter cube. The concentration of the bacteria will reduce as fresh water enters the lake. Obviously, it will dilute fresh water. More fresh water will dilute the bacteria, the concentration of bacteria. So the differential equation that governs the concentration C of the pollutant as a function of time in which is given by dC per dt is equal to actually negative 0.06 C. The initial concentration of bacteria is 10 to the power of 7 parts per meter cube. So using Runge-Kutta fourth order method, you're asked to find the concentration of the pollutant after 7 weeks. Take a step size of 3.5 weeks. Of course, if you take a step size of 3.5 weeks using 2 iterations, you'll just arrive at the final answer. But I'm going to demonstrate this same problem using the step size of 1 week. You would have more computational time, but a more enhanced solution. So dC per dt is negative 0.06. And here the coefficient is negative 0.06. T0 is 0. I'm going to use delta T as 1 week. Initial concentration 10 to the power of 7 actually. So let's start now. So for the first week, initially the concentration is 10 to the power of 7 and the coefficient for its different derivative is negative 0.06. Let's first find K1. K1 is the slope at T0 and C 10 to the power of 7. That's the initial concentration. So all you have to do is negative 0.06 times the concentration you have to multiply. This would give you, this time the initial concentration shall give you K1. Now K2 is the value at time step of T plus delta T over 2 and concentration of Ci plus half K1 times delta T. So that's the slope at T plus delta T over 2 times and at concentration of Ci plus half K1 delta T. So we know K1 already. We can compute C1 or C0 plus half times K1 delta T, which is essentially C0 plus half times K1 times delta T here is of 1 weeks. So at this concentration and time of T plus delta T, which is 0.5, we're going to calculate the corresponding value of K2. Of course, the derivative doesn't depend in this specific example on T. So computing the T0 plus delta T over 2 is not useful as such. So the value of K2 is essentially this computed value of C at halfway between 0 and delta T time steps and at a concentration of Ci or C0 plus half K1 delta T. So using that concentration times that coefficient, it shall give you this value of K2. And the next, similarly, we are going to find at T plus delta T over 2, and at the concentration of C naught plus half K2 times delta T at this concentration, which is C plus half K2 delta T. That's at this concentration at the time of 0.5 T naught plus delta T over 2. We are going to calculate the slope, or K3. So essentially that this concentration times that constant, and then we are going to find at delta T, the slope at delta T, at the T plus delta T instead. So at the end of the time step, which is C naught plus K3 times delta T, and then we are going to compute the slope, which is essentially the coefficient times the C, which we have computed here. And then ultimately, at the end of the time step, using the Runge-Kutta method, the concentration shall be C naught plus 106 times K1 plus twice of K2 plus twice of K3 plus K4 times delta T, which is 1 week, shall give you the concentration at the end of the time step. Once you find the concentration at the end of the time step, here we are going to put the value, which is at the beginning of the next time step. The value at the end of the first time step is going to be the value at the end of the next time step, right? So the value at the end would be the value at the beginning for the next time step, actually. So that's it. Now you can just populate this. So you can just populate that. You can obviously see at the end of the 7th week is going to be 6.57 times 10 to the power of 6. So this is the final answer. As you can obviously see, this concentration is not still below the acceptable level, because the acceptable level is 5 times 10 to the power of 6. But what we have found is 6.57 times 10 to the power of 6. Now you are requested to continue this computation when, after how many weeks will it be below the acceptable level of pollutant concentration. So you need to continue that computation and find that value or period at which it is below or equal to 5 times 10 to the power of 6 parts per meter cube. So that was another example using Runge-Kutta. Another example is a 100-meter wide vapor carries a flood discharge of 600 meter cube per second. The river bed has a slope of 10 to the power of negative 6 and a bed roughness of n equals 0.02. A dam is built across the river to a height of 50 meters. Find the depth of water at 50 kilometers upstream of the dam using Runge-Kutta fourth order method. Use the gradually varied flow equation. Refer on the gradually varied flow for flow profiles. We have talked about this equation when we talked about the gradually varied flow equation, and we have, of course, done part of this problem as an example there. So dy for dx is equal to bed slope minus friction slope over 1 minus power number square. Or you can represent this like S naught minus SF over 1 minus discharge square times top width over acceleration due to gravity times cross-sectional area cubed. Or you may also represent this like S naught minus SF over 1 minus specific discharge square over G times depth cubed. The friction slope, you can obtain it from Runge's equation. And specific discharge is Q over P, actually. So remember we were talking about this equation when we talk about the gradually varied flow. So that same equation we are going to use and try to solve the problem or the depths at a certain point upstream. So we have talked about the different water surface profiles. In your assignments, you were asked to solve this set of problems, remember? Yeah? One of which is this equation, this problem. Mind you, one of the students was asking me about how we can determine the channel slopes. It is clearly established that you need to compare the normal water depths and the critical water depths. The normal water depths you can compute from Manning's equation, and the critical water depths you have tried to derive that. It's the cube root of q squared over g. So you just compare the normal depths and the critical water depths. So long as the slope or the bed slope is not negative, in which case the channel slope is going to be categorized with adverse category, or so long as the channel slope is not 0, in which case we are going to classify it as horizontal. Then so long as there is a positive slope, then the classification of the channel slope would either be mild slope or steep slope or critical slope. If the normal depth exceeds the critical slope, the critical depth, then it's mild slope. If the normal depth is less than the critical depth, then it's a steep slope. If the normal depth is equal to the critical depth, then it's critical slope. You don't have to look at the actual depths. Just look at the normal depths and the critical depths. The actual depths would be helpful once you decide the channel slope. It's helpful to categorize the zone. Is that in zone 1 or zone 2 or zone 3? Let's say while it is in mild slope. If y exceeds both normal depths and critical slope, critical depths, then it's going to be M1. If it is between normal depths and the critical depths, then if y is between the two, then it's going to be M2, in which case there would be a drawdown. So it's decreasing along the flow path. Drawdown, subcritical flow, and there will be a drawdown in that case. If y is less than the normal depths and the critical depths, then it's going to be M3. There will be backwater and it will be supercritical flow. Whereas in case of M1, there will be backwater again, but that's subcritical flow. The depth actually exceeds, the depth is larger, so obviously the velocity is smaller. But in M3, the depth is smaller and the velocity will be larger, supercritical flow. So we're going to do this problem, continuing from the discussion we had earlier. Remember, we're trying to work on this problem. So the weight is given to be 100 meters, Q is 600 meters cubed per second. That's the bed slope. Manning's roughness coefficient, 0.02. So you can easily calculate Q, which is capital Q over B. At the end of, a dam is built at the end of the channel with a height of 50 meters. Using this value of specific discharge of 6, you can easily calculate Y critical as cube root of specific discharge square over G. So Y critical is basically that square over G cube root. So you know Y critical to be 1.54. The normal depths, in order to be able to deliver this much discharge, you have to iteratively calculate using Newton-Raphson, which we did last time, remember? For an assumed value of Yn, if you just give here just one depth, yeah, then the area is going to be like 100 times that depth. And this is going to be the perimeter, which is twice of the depth plus the width. And then this is the area of the perimeter, which is the hydraulic radius. And then the estimated discharge using Manning's equation here you have. And then that's the error of what's estimated using Manning's equation and what it is supposed to carry on. So that's the error. So we want to reduce the error. If you just keep on increasing that, it will just keep on reducing the error actually. But we need to calculate using Newton-Raphson technique. Yeah, so using Newton-Raphson technique, using solver, we have tried to solve that, remember? So we are going to set objective function, which is the error, to be 0 by changing what? The value of Y here. By changing this value. Yeah? So we say solve, then it would quickly find it to be solution has been found. So it's obviously the normal depth is 20.25. So at the end of the channel, Y is the actual depth is 50 meters. The normal depth is supposed to be 20.25. And the critical depth is 1.54. Now we just look at the first two, Yn and Yc. Looking at these two values, you can decide whether it is mild slope. Obviously, Yn exceeds Yc. So it's mild slope. And Y exceeds both Yn and Yc. So it is M1 zone in that case. So we can easily identify slope, channel slope, and the zone. With M1 zone, then we expect backwater effect and subcritical flow. Of course, you can easily find these values from the ratio of dy per dx here. Right? So you know already the value of S naught, you know it, and then you know SF. Since Y exceeds Yn, then obviously you can just obtain the sign for S naught minus S. And since you know Yn, Y exceeds Yc, you know it's going to be subcritical. If it is subcritical, obviously Proud number is less than 1. So we can easily identify the sign for dy per dx, whether it's going to be backward. If it's positive, then it's going to be positive ultimately. So that would give us a positive sign. So it's increasing along the flow direction, obviously. So under such circumstance, the dam is a downstream boundary condition. Yeah. So the flow decreases. The flow decrease upstream, or it's just increasing when you just go to the dam, obviously. So using Runge-Kutta method, let's first find the 4 slopes. Let's first find the slope, which is obviously the ratio of dy per dx here. That's the slope, obviously. So using these known values for S naught, You can easily calculate here SF using this value, specific discharge square times winding roughness coefficient square over normal, the actual depths square times hydraulic radius, the power of 4 over 3. So we know SF already. So since we know SF, we can easily calculate dy per dx. So that should give you the value of K1 here, which is S naught, bed slope, minus the friction slope, over 1 minus Q square over acceleration due to gravity times depth cubed. So that's K1. Yeah, at the initial point, at the dump site. Next, we are going to calculate somewhere. You're asked, by the way, to calculate the value at 50 kilometers, which means at h is equal to 50,000 meters. So the next value for K2 should be estimated at x is equal to x plus half of h. H is 50,000, so at like 25 kilometers upstream, actually, if you want to do it at one go. So in that case, first let's calculate y. Y is yi plus half times K1, which we have calculated here, times h. So this is essentially 50 plus K1 times h over 2. So that's y. Using this value of y, we can calculate the area, which is width times y, and then perimeter, which is width plus twice of y, and then hydraulic radius, which is area over perimeter, and then the friction slope, using the same set of equations which we have used up here, which is q square, n square, y square is going to change this time, and then the hydraulic radius is going to change this time. Yeah, so we are going to calculate here first SF using this value of depth and this value of hydraulic radius, but all the rest of the stuffs are the same. So we find the friction slope. Once you find the friction slope, then you can calculate K2, which is dy per dx, basically. So dy per dx is the bed slope minus the friction slope, which you have computed, over 1 minus q square, which is specific discharge square, over acceleration due to gravity times y cubed, which is the y which you have computed. So that's K2. Once you find K2, let's go to K3. Using this value of K2, we're going to calculate first y, which is y initial, which is 50 meters, plus K2 times h, at 50 kilometers actually, over 2. So that's y. Using this value of y, you just calculate A, you just calculate P, you just calculate R, and then you just calculate SF. SF would need the R, which is calculated here, and the Y is calculated here. So using this value of SF, that's the friction slope at K3. And then you can easily obtain K3, which is dy per dx, which is the bed slope, minus the friction slope, which you have computed, over 1 minus q square over g times depth cubed. So that's K3. So it's also midway between the downside and at 25 kilometers upstream. And then ultimately at 50 kilometers, it's going to be like yi, which is 50 meters, plus K3, which you have computed, times h, which is 50,000 meters. Using this value of depth, you can easily obtain the area, the perimeter, the hydraulic radius, and then ultimately the friction slope. And then using this friction slope, you can easily obtain K4. Once you find K4, using Runge-Kutta method, we are going to find the weighted average of the slopes. So 1/6 times K1 plus twice of K2 plus K3 plus K4 times H is Yi. But mind you, this equation is meant to find out given initial estimate of Yi minus 1. We are going to obtain Yi. But in our case, we are going to find Yi is known already. It's going to be 50 meters. And we want to find Yi minus 1. That's one thing. You know that it's going to increase. Or you may just obtain, since we know it's going to be backwater effect, you know the height upstream is going to be lower than the value downstream. You can just deduct from 50. Yeah? So that should give you these values now. Once you find these values, and then deduct it from 15, which is from 50 meters minus those values, weighted average of those values times H. Then this should give you here depths of 49.95 upstream. So this is with at 50 kilometers. If you have done the same problem progressively by working at smaller values of H, maybe at 10 kilometers, and then 20 kilometers, and then 30, 40, 50 ultimately, you would have a more enhanced version of your ultimate answer a little bit. Yeah, so I was trying to work with different depths here, and then ultimately I found different answer. So you are requested to work with the same problem, but for smaller spatial scale. So that was the case for Runge-Kutta for order method. Runge-Kutta of first order could be considered like Euler's method. So in a way, Runge-Kutta is a more general form in solving numerical equations, one of the more general forms in solving numerical equations, numerical problems, numerically to solve ordinary differential equations. Now we talk about partial differential equation. As you know, partial differential equations involve partial derivatives of unknown functions are two or more independent variables. In ordinary differential equation, we're dealing with one independent variable, but here, two or more. So, you can see on the examples here, u depends on x and u depends also on y. If the dependent variable is not squared or is not multiplied with itself, then we call the partial differential equation to be linear. Otherwise, it's not linear. So here in this class, we deal with linear, second order, partial differential equations because of their wide application in engineering. Of two dimensions. It's two real variables. Huh? So the general form is capital A, second partial derivative of u with respect to x, plus big capital B times second partial derivative of u with respect to x and with respect to y, plus capital C times second partial derivative of u with respect to y, plus capital D times partial derivative of u with respect to x, plus capital E times partial derivative of u with respect to y, plus capital F times u is equal to 0. It's a very general form. for representing partial differential equations. Now we are going to evaluate the coefficients b squared minus 4ac. That would enable us to classify the partial differential equations into three major categories. If the value of b squared minus 4ac, mind you, the b, the a, the s, the c are the coefficients in that partial differential equation. So if b squared minus 4ac is less than 0, we call it elliptic partial differential equation. If b squared minus 4ac is equal to 0, we call it parabolic partial differential equation. If it is greater than 0, we call it hyperbolic partial differential equation. Typically, this elliptic partial differential equations is more of problems which have reached an equilibrium, like Laplace equation, steady-state equations. It's two spatial dimensions, or of course you can talk about three spatial dimensions, but for standing in this class it's two spatial dimensions. Whereas diffusion equations is one time variable and one spatial dimension is parabolic. Because b squared minus 4ac is equal to 0 in this case. You can clearly see in Laplace equation the coefficient of is going to be the groundwater height. In the groundwater hydrology, you might have come up with this type of equation, Laplace equation. Yeah. So you can see the coefficients of the second derivative with respect to x, that's a is 1. And the coefficient with respect to the second derivative of u with respect to y is c. So c is also 1, a is 1, c is 1, but b is 0. So b is 0, obviously, so a is 1 and c is 1, so ultimately b squared minus 4ac is going to be negative. Negative, huh? In case of the parabolic equations, of diffusion equations, second derivatives along the x spatial dimension, along the spatial dimensions, along x. So the coefficient is k here. So a is k, b is 0, c is 0. Since c is 0, so 4 times a times c is 0. So see, b is 0 already, so b squared minus 4c is going to be 0. The other one is hyperbolic equation, typical wave equation. Here, there is one time variable and one spatial dimension. So a is 1, c is 1 over c squared. Since c squared is positive, you just take it to the other side to make it similar in structure with the general form is equal to 0. So you can see here a is 1, the coefficient pertaining to second derivative with respect to time is negative 1 over c squared. C squared is always positive, so negative 1 over c squared is always negative. So the coefficient c is always negative. So 4 times a times c is going to be negative 4 times a times c is going to be positive. And b is going to be 0 here. So that should give you b squared minus 4ac to be positive. So this is hyperbolic partial differential equation. Very much common type of equation in hydraulics, especially with Saint Valence equation. Many of the first order partial differential equations are hyperbolic in nature. Wave equation, pure advection equation, those are hyperbolic equations actually. Now, the b square minus 4ac term, when it's less than 0, we said it's elliptic category. It would have a characteristics curve of no real characteristics or paths. Essentially, this is a problem which has arrived at steady state. So essentially with elliptic, partial differential equations, you can see the range of dependence and range of influence. There is no clear domain of dependence and the range of influence here in case of elliptic. In case of parabolic, there is all the present and past times would form the domain of dependence. All the present and future times would characterize the range of influence. So in case of parabolic partial differential equations, at each time or time-like variable, all points are dependent on all other points. There is infinite propagation of speed or spread of information. Whereas in hyperbolic partial differential equations, there is a finite domain of dependence. Within the characteristics curve, there is a finite information propagation. So there is a very clear domain of dependence, range of influence in case of hyperbolic partial differential equations. So there are two real and distinct characteristics paths. In case of parabolic, it's one and repeated characteristics path that would propagate with infinite speed. But in case of hyperbolic, it's finite domain of dependence and a finite information propagation with a finite speed. So two real and distinct characteristics paths. So you can see the method of characteristics is essentially applicable for hyperbolic type of partial differential equations. Now, as you might remember, when we were talking about method of characteristics, we have said there are different requirements for boundary conditions in case of hyperbolic partial differential equations when we were discussing with the method of characteristics. So earlier we talked about method of characteristics. So we said in method of characteristics, here we have tried to show subcritical flows will require one boundary condition either at upstream or downstream point or at both of them, but just one boundary conditions. But in case of supercritical flow, two boundary conditions either at upstream or if the flow is moving the other side at downstream. So of course, in any case at upstream, if it's a negative flow, then it's going to be on the other side, but it's always going to be on the upstream side, but two boundary conditions for supercritical flow. But for subcritical flow, just one boundary conditions at both sides. the left side and at the right side. So case A and case B would tell you the supercritical flow, computational domain for supercritical flow, whereas the third case, in case A, the third case would tell you the subcritical flow, computational domain for subcritical flow, basically. Remember, using method of characteristics, the initial conditions are important to fulfill the method of characteristics. But for the case for parabolic equations and for elliptic equations, we need to have boundary conditions both on the upstream and downstream side are important. In case of elliptic, since time is not there, so we specify boundary conditions along every path. In case of parabolic and hyperbolic, there is no boundary condition from the top. So we typically talk about marching problems. It's propagating along that direction of time. But in case of elliptic equation, it's not propagating along the y-axis because the y-axis is not time here. So we do have boundary conditions along every path. That's at equilibrium condition. It has achieved already equilibrium condition. Now, finite difference elliptic equations. In case of elliptic equations, b square minus 4ac is obviously less than 0. So in solving partial differential equation, we should always be able to identify the type of the PDE first, using p square minus 4ac. If no real characteristics exist, then there is no preferred path of information propagation here. So the domain of dependence and the domain of influence, or zone of dependence and zone of influence of every point in the entire solution domain here. So Laplace equation, which we typically use in groundwater, is elliptic equation, basically. For the case with sources and sinks within the 2D domain, we can also represent this as Poisson equation. Obviously, in elliptic equation, there is no time. Time independent. Flow in porous media, or temperature in typically in thermodynamics could be represented along different directions. Could be represented using Laplace equation. So second partial derivative of the hydraulic head along x plus second partial derivative of hydraulic head along y is equal to 0 at equilibrium from continuous principle. So you can easily derive that from Darcy's law. Using continuous principle, you can easily derive this Laplace equation actually. Now you can evaluate using finite difference representation of each one of these second partial derivatives. You can easily represent this set of equations. We're talking about first order approximation of the second derivative with center difference here. I think last time it was erroneously put this equation, but honestly the second derivative with center difference, proper equation, there was some typological error there in the last lecture. Obviously from equation 5.2 4, then obviously the result would be equation 5.25 as illustrated here. So the second partial derivatives would involve the value at I plus 1, the value at I, and the value at I minus 1. So the value at I plus 1 minus twice of the value at I plus the value at I minus 1, and then divided by delta x square. That's along the x-axis. The second derivative with center difference. This is second order accurate. So you're going to use this equation to calculate using elliptic partial differential equations along both directions. Mind you, here we are going to represent the i's direction, the nodes by I. Along y direction, we are going to represent this by j. Later, when we talk about parabolic or hyperbolic equations, the time domain, we are going to represent it by n now. So also when we say x plus delta t, x plus delta x, so we say I plus 1. Y plus delta y, then we say j plus 1. Then x is going to be represented like I, y is going to be represented as j, and x minus delta x is I minus 1, y minus delta y is j minus 1. Later when we talk about time, we'll just represent t as n, t plus delta t as n plus 1, t minus delta t as n minus 1. So, similarly representing using the center difference which I have described earlier, h at I plus 1 along the x-axis, j is constant. So at h at I plus 1 minus twice of h at I plus h at I minus 1, j is constant along the horizontal axis over delta x squared. And second partial derivative of h along y with respect to y, this time I is constant. So j plus 1, h at j plus 1 minus twice of h at j plus h at j minus 1 divided by delta y squared is the finite difference representation using center difference of the second derivatives. Mind you, both of these terms are second order accurate. So if you just add the two to establish this Laplace equation, then you can find an equation of order delta x squared and delta y squared. Now, if you assume delta x and delta y to be uniform or equal, then you can omit the denominator. Then you would end up with hi plus 1 at j plus hi minus 1 at j plus hi j plus 1 plus hi j minus 1 minus 4 times hij is equal to 0. This is typically called the Laplacian difference equation. Given the values at the all the surrounding nodes, given the boundary conditions all around, then you can easily solve this Laplacian difference equation. But it's important that it should be given with these boundary conditions. Remember, with elliptical equations, all the surrounding boundary conditions need to be provided. Some people call this equation 5-point finite difference equation. Obviously, there are 5 points here. Yeah. So using those 5 points, you can easily solve the values of h at each one of the nodes. But the boundary condition could be specified in different form. It could be specified as a constant value, which is Dirichlet boundary condition, or it could be provided as a derivative, which is Newman's boundary condition. or it could even be a mixture of the two. And the finite grid spacing need not necessarily be of the same magnitude. Delta x may be different from delta y, in which case you can represent beta as delta x over delta y. And then the equation would look like, for all interior nodes, hi plus 1 at j plus hi minus 1 at j plus beta square hi j plus 1 plus beta square hi j minus 1 minus twice of 1 plus beta square times hi comma j is equal to 0 if delta x and delta y are not the same. Obviously, in this relationship, if delta x and delta y are the same, then the beta is going to be 1. And negative 2 into 1 plus beta square is going to be negative 4. Then obviously this equation would reduce to this equation. So using this equation, you can easily solve for each of the interior nodes and using the specified boundary conditions. Then you can find the values at each of the interior nodes, the values of the variable actually. Now, next class, we'll talk about how to solve. There are different types of solution methods for solving these linear algebraic equations. You may either use direct methods like Gauss elimination and Thomas algorithms. These are relatively easier methods which you know from your numerical courses, but these are susceptible to round-off errors. Or you may use iterative methods like Jacobi iteration, or Gauss-Seidel iteration, or successive over relaxation or SOR method, or alternating direction implicit technique. But most of these techniques, I hope you have learned in your numerical courses. I'm not going to repeat, but just successive over relaxation is put in the annex part. So you can see in the annex part here, successive over relaxation has been described. So you can carefully go through that material. So next class, we'll talk about this example to find the values at the interior nodes, the values of the temperature actually. Or you can just take it as ground root of head at each of the interior nodes. Thank you for now.